Logarithms can also be used to manage and explore nonlinear data in trends. Two common nonlinear relationships are polynomials, such as y equals ax to the power of n, or exponentials in the form y equals ab to the power of x, where a, b, and n are constants. Given values of x and y, we can then use logs to determine the form of the relationship and find values for each of these constants. This scales down the y values and converts the relationship to linear ones that are easier to read and plot. So if we look at our first case, so polynomials, y equals x to the power of n, we start with a nonlinear relationship. If we take logs of both sides, this gives us log y is equal to log ax to the power of n. And using our log multiplication law, we can write it as follows. Then using the power law, we can bring down the n in front of the log. If we compare this to the common form of a straight line, y equals mx plus c, y is equal to log y, n is equal to m, our gradient, and log x is equal to x, the variable, plus the constant c, which is the same as log of a. If we plot this, we will plot the graph of log y against log x, and we get a straight line as shown here. The straight line has gradient n and vertical y-intercept log a. If we look at our second case, exponentials, so of the form y equals ab to the power of x, again we take log of both sides, use the multiplication law and the power law to give us log of y is equal to log a plus x log b. Again, if we compare this to the common form of a straight line, y equals mx plus c, y is equal to log y. Our gradient is now log b, so m is log b. X is just x, and our y-intercept c is log a. This time we plot the graph of log y against x, and we get the straight line with vertical intercept log a and gradient log b. For this question, part A simply wants us to draw a table containing the values of log x and log y. So log x and log y. So when x is 10, if we use our calculator, we work out that log x is equal to 1.00 to 2 decimal places. Log of 20 is 1.30 to 2 decimal places. Log of 30 is 1.48. Log of 50 is 1.70. And log of 100 is 2.00. We can do the same for log y, so if we put each of our y values in, so first of all 88, we get 1.94. Log of 232 is 2.37. And if we do this for the rest of our values, we get 2.61, 2.92, and 3.34. So for part C, we need to plot a graph with log x on the horizontal axis and log y on the vertical axis. We can then put a scale on. So the vertical axis needs to go up to 4 and the horizontal axis needs to go up to 2. So we'll just carry it on with our label. So 1, 2, 3. And then we can plot each of our points. And we can draw a straight line through them. For part C, we need to use our graph to estimate the values of a and n. So we're going to start with our original equation and convert it to a log relationship. So if we take logs of both sides, we get log y is equal to log of ax to the power of n. We can then use our addition rule. So we still have log y is equal to, and then we can split this term into log of a plus log of x to the power of n. And then using our power rule, we can bring down the n to give us n log x for that final term. If we compare this to our general form y equals x plus c, then we get that log a is equal to our y-intercept, which if we look at our graph is approximately 0.5. And using our log rules, this tells us that a is equal to 10 to the power of 0.5, which is approximately equal to 3.16 or 3.2 to two significant figures. We can do the same for n. So looking again at our log equation and comparing it to y equals mx plus c, we can see that n is our gradient. So n is our gradient. So if we use the two endpoints in the table, here and here, we can find the gradient by doing the difference in log y divided by the difference in log x, which is equal to 3.34 take away 1.94 divided by 2 minus 1, which is approximately 1.4 to two significant figures. For part A, we're asked to find the equation of the straight line. So given our equation, y equals ab to the power of x, we can write this in log form now. So if we take logs of both sides, we get log y is equal to log of a b to the power of x. We can use our multiplication rule to write this as log y is equal to log of a plus log of b to the power of x, and our power rule to give us log y is equal to log of a plus x log b. From our graph, we know that the y-intercept is 3.1, and if we compare our log equation to the equation y equals mx plus c. We know that the y-intercept is given by log a. So log of a we know is 3.1. We also know that the gradient is given by log of b. So log of b is equal to the gradient, which is 1.25. This gives us the equation log y is equal to 3.1 plus 1.25x. Part B, we need to write it back in power form. So we get y is equal to 10 to the power of 3.1 plus 1.25x, which we can split up and write as y is equal to 10 to the power of 3.1 times 10 to the power of 1.25x. The first number we can work out, so 10 to the power of 3.1 gives us 1260 times 10 to the power of 1.25, and I'm going to take the x outside of my bracket, which again allows me to work out that as a number. So 10 to the power of 1.25 is 17.8 to the power of x, which means if I compare this to my original equation, y equals a b to the power of x, then a is equal to 1260 and b is equal to 17.8. Part C wants the meaning of a in context of a model. So a, which is 1260, is the initial size of the patch of algae. Now try textbook exercise 14H on page 331. Questions 1, 2, 3 and 4. Make sure you come and see any of your teachers if you need help with this before it's due in.